Dimitri Sprayregen. We're from South Florida in the USA, and today we're going to be discussing the tracking and mitigation of space debris using nanosatellites in a low Earth orbit. Dimitri and I are both part of the Wolfpack, or the Wolfpack CubeSat Development Team. We are a group of middle through university school students that are frequently launching high-altitude balloons. We were also in 2018 selected by NASA's CubeSat Launch Initiative program and launched our first CubeSat known as WISeSat-1. Since then, we've launched one other CubeSat, and we have one more CubeSat scheduled to launch later this month. And finally, late 2025, we have our fourth CubeSat to be launched. CubeSats are part of something known as the nanosatellite family, a miniaturized size of satellites used for space research and applications. CubeSats specifically are 10 by 10 by 10 centimeters and weigh just over 1 kilogram. Nanosatellites, or CubeSats in our case, are more cost efficient or effective, as less development time, less money, and less resources are put into the creation and development of the mission. Space debris is rapidly increasing, causing many problems in space. With the exponential growth of the space debris, tracking for patterns and habits and the mitigation of the space debris becomes more and more imperative as time goes on. The two charts below can show the exponential growth of predicted numbers for space debris in years to come. As of now, or as of January 2022, over 9,000 metric tons are currently in space orbiting. With the growth since the 1960s in both space debris and satellites, with over 10,000 satellites today, the collisions between the two become more and more likely as time goes on. For those reasons, fast, efficient, and effective space travel becomes more and more crucial. Space debris can orbit at over 8 kilometers per second, increasing cost operations for the precautions put into defending the satellite itself. With damage to possible equipment such as solar panels on the outside of the satellites, the cost for operations of the satellite becomes more and more costly.
Currently, the main system that is responsible for tracking space debris in Earth's orbit is the Space Surveillance Network, or the SSN for short, which is operated by the U.S. Space Force's Delta II in California and the European Space Agency's Space Surveillance Team in central Germany. The main job of the SSN is to track artificial objects in Earth's orbit, which includes space debris, and map it, which is done using radio frequencies and electro-optical sensors. The main capabilities of the system allows the system to track objects 10 centimeters and above in size. However, this limit is where the main shortcomings of the system become the most evident, as the majority of space debris in Earth's orbit is far too small or too far out of range to be adequately tracked, which is where nanosatellites come into play. Technologies that are already used in tracking systems can easily, plausibly, and effectively be applied to nanosatellites. Light detection and ranging, or LiDAR for short, is one of the numerous technologies that can be applied to nanosatellites effectively and versatilely, alongside radio frequency technology for tracking space debris. LiDAR works by emitting short laser pulses in its surroundings. These laser pulses reflect off of target objects, in our case, space debris, and return to the satellite, which the LiDAR system can detect and can use to measure and map information with high precision. This base information includes things like the distance of the space debris from the tracking satellite and the visual shape of the debris. With a network of these tracking satellites in different types of orbits and positions, the information collected from the LiDAR sensors can be used to determine things like the debris' specific location, the debris speed, and the debris' overall risk factor. Moving on to the debris mitigation itself, Astroscale's technologies are some of the most innovative solutions when it comes to debris mitigation and satellite life extension. Since the company's inception in 2013, the main goal of the company has been on the reduction of space debris in Earth's orbit. Notably, the company has recently achieved a $1 billion market capitalization since the company went public on the stock exchange in May, alongside hundreds of millions of dollars worth of funding over the years. Astroscale is in development of 4 different services, with 2 of these specifically relating to the direct removal of space debris. Astroscale's End of Life, or EOL service, and Astroscale's Active Debris Removal, or ADR service. Astroscale's End of Life service utilizes a nanosatellite equipped with infrared cameras and LiDAR sensors to deorbit a targeted inactive satellite as a chaser satellite. First, the chaser satellite goes under an inspection process of the target satellite and matches the tumble rate of the target satellite. Oh, hey. Where was I? First, the chaser satellite goes under an inspection process of the target satellite and matches the tumble rate of the target satellite after a target has been identified. After that, the chaser satellite attaches to the target satellite using magnetic plates equipped on both satellites and a docking device on the chaser satellite. After that, once the two satellites are finally attached, the chaser satellite uses optimized chemical and electric propulsion jets to lower the altitude of the two satellites to a release orbit where the target is let go of. For the ADR service, the process works similarly to the EOL service, which uses the same inspection process as the EOL service, but uses a specialized robotic arm to attach to loose space debris instead of magnetic plates. In 2023, NASA released a research report detailing on the concept of debris remediation and the cost of moving and removing space debris. For mitigating smaller debris, NASA had one solution that stood out in relation to nanosatellites, which is space-based laser systems with laser ablation and small satellites, which are satellites that weigh less than 1,200 kilograms. Lasers and other forms of directed energy can be used to transmit force onto another object without making physical contact with that object. With laser ablation, laser pulses are fired at an object in rapid succession to slowly remove from the material of that object. After a material has been successfully ablated, byproduct material consisting of mostly plasma and gas is released, which contributes no further debris to Earth's orbit. Experimental data and simulations of this concept have shown that this method can work on both trackable and untrackable debris when passive debris detection is employed on the spacecraft itself, which is a significant advantage of this system over other mitigation methods.
In order to understand these mitigation methods and why space debris is becoming such a large problem, there are three methods or syndromes that you need to understand. The first of the three is the Kessler syndrome, or Kessler theory. Created by Donald J. Kessler in 1978, the Kessler syndrome explains the rapid increase of space debris since the 1960s. This syndrome essentially states that the more debris there is, the more that the Kessler syndrome acts. As objects orbit, in our case Earth, and collide into each other, more and more space debris is produced. The next method is the net and capture method. Created by Airbus Defence and Space, which is a smaller division within Airbus SE, this method uses a net attached to the back of a satellite, or in our case, a nanosatellite, to collect debris. Although there are potential for structural breakdown if too large of a satellite is used, nanosatellites, when equipped with this method, could be much more effective and efficient. Next, the deorbiting method, which was created by Dr. Jerome Pearson, as he states it in one of his earliest papers in 1974. Evolved over time by entities such as NASA and the European Space Agency, this method works by activating a thermal runaway. This thermal runaway produces red-hot gases, which are then channeled into produced energy. When enough energy is created, enough thrust is created used to deorbit space debris.
For the numbers on the amount of debris mitigated, the statistics depend on the mitigation method. For the net method, it has been estimated by the ESA to be able to remove between 100 to 200 tons of debris per year. For the net method, it has been estimated that between 10 to 20 medium or large objects, like decommissioned satellites, can be removed per year with current net technology. For the space-based laser system mentioned before, it has been estimated that over 100,000 pieces of debris can be removed over the satellite's lifetime. Claude R. Phipps, the developer of the space-based laser concept referred to in the NASA report, stated that it would cost around $300 per object made out of light metal to remove. For objects that a laser would break apart less easily, it has been estimated that it would cost up to $3,000 per object at the most to remove. Although the concept of a space-based laser system has the potential to be applied to nanosatellites in the future, the sheer cost of operating such a system leaves the system unattractive compared to other previously mentioned methods for employing in an active mitigation program early on.
In the end though, it's the future impacts that really make a difference. With safer access to orbit for all spacecraft, with the mitigation of debris, this is a great advantage to have in the future. In addition to this, the less danger to crewed missions are also a greater advantage, with also increased exploration cadence. With missions such as Journey to Mars by NASA, the reduction of space debris becomes crucial as problems like overpopulation, climate warming, and threat to war becomes more and more likely. That is why the colonization of different planets seems to be more of a reality for Earth than imagination. With that being said, are there any questions?